Okay, I'll give you that new sheet today from the notes, page 26B and C. So we talked about 26B in class. Here's 26C. 26C talks about up and down. How does hill ball accelerate? And again, this is really accessing what it means to have negative acceleration and what it means for velocity and acceleration to be aligned or opposed. So basically, here's a scenario. We have a ball that is rolled up a hill. Come over here, I'll show you how this works. All right, here's the ball. Here's the hill. Husky, fan, steady, and baby are on hand to watch. Sorry, tank card is off flying around trying out those new wings. Anyway, what I'm going to do here is I'm going to give the ball a push. Actually, I'll give it a flick. Roll up, it'll come back down. So one more time, ball gets a flick, rolls up, comes back down. Now, we are not actually concerned with the flick itself. The ball gets a flick, which will give it some speed, and then it starts heading up the ramp. And at this point, we will start the problem. The ball will go up the ramp, reach a peak, the ball will come back down the ramp, we'll stop the problem before it quite hits the bottom. So there it is. That's what you're seeing live, which is actually going to happen. Now, if we watch this closely, what you will see is the following. We don't need this over here anymore. But let's pull up. Here it is. Okay. So here this is in slow motion. I'll frame advance. So this is the ball got a flick, and now it is heading up the hill. At this point, I started marking the center of the ball roughly with a dot. So I did my best to mark each frame. There's the next center, there's the next center, there's the next center. You notice, of course, the ball is blurry. So it's a little difficult to identify exactly where the center is, but I did my best estimating. That's one thing to notice, by the way. When an object is blurry in a video, when you're looking at the frame, so the object is blurry here actually in the picture, you know it's moving fast. As it goes up the hill, there are a few things to notice. One, look at the blurriness. Less. Now the ball is actually very clear. Well, that means it's moving slowly. Well, that actually, let me go backwards here, backwards in time. That actually fits perfectly with what we have estimated. So it starts out, the ball is moving fast. So at the beginning of our problem, at t equals 0, the ball already has an initial velocity, and it's moving quickly. So it has a high initial velocity. Then as it goes up the hill, you will find its velocity decreases, as evidenced by smaller and smaller spaces between the dots, between the blinking lights, and as evidenced by the clear image of the ball at the top. Then, once the ball is at the top, it actually begins to come back down. And what you will see is the blurriness increases and the spacing increases once again, more or less laying right over where it was before and ending down there at the bottom. So we have, roughly speaking, the same pattern up and down, which tells us a lot. We have the blurriness at the bottom, the crispness at the top, tells us a lot. Let's go over and check this out. Get off that. There it is. Okay, so let's sketch this out. Now, I know one of the classes, we started drawing it to the right. I'm going to draw it to the left to match the video, but you're more than welcome to keep drawing it to the right. It doesn't matter. It doesn't change anything. So here's our scenario. Actually, we can do the shape drawer. Wouldn't that be nice? Sorry, you don't have a nice shape, but here. So our ramp, let me edit that. Our ramp is not that steep. Maybe it'll let me drag this thing out a little bit. Good. So draw yourself a little triangle. There it is. That's like our ramp right there. Cool. Now, the ball is going to go up the ramp. I'll stick to just drawing at this point. So you should draw this on your page. Put the ball down here at the bottom. Now, at this point, the ball already has velocity. The ball already has velocity directed up the ramp. VI. Already directed up the ramp. And we're going to put our blinking lights on this. It already has the first blink is right here. Fine. Now, we mentioned this earlier, but before t equals 0, the ball was pushed, in this case, parentheses, by my hand. And that's what actually provided it, the VI. Anyway, the ball was pushed by the hand. That's what actually provided it, the VI. Cool. Now, let's keep going over here. What happens to the ball as it goes up the ramp? Well, we already saw that. We already had a look at that. When the ball goes up the ramp, the pattern, oh, that's not the one. Here it is. The pattern starts out spaced and it becomes more narrow as it goes up the hill. Okay, that's actually no surprise for us. There's a reason for that too. So let's plot this out. If you remember the way we did this, it may actually help you to see what I'm doing. So let me bring the view back over here, and I'll turn this up to the board. Maybe it'll help you just get an idea of what I'm doing in terms of how you map this out. But you're not going to have to draw this. However, you may have to draw some, but you're not going to have to draw this one. Odds are you would select this from multiple choice. Anyway, if I know that it's starting down here and it's ending up here, I'll put a dot up here somewhere. Here's my ending dot. Let me do that in black. Put a dot up here. Fine, that's where it's going to end. Now, we also know that it was faster at the bottom. So our trick was always split the difference. So take here, the middle of this, roughly speaking, let's say is somewhere around here. Then if it's faster at the bottom, the right side will always get the bigger spaces, the left side will always get the smaller spaces. So split the difference again, put up here on the left side, split again, split again, split again. That's probably enough. The only one here that's false is the very top one, because here you have a distance. That distance gets smaller, 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 and then that one would actually be the same. So we needed that last dot to actually help us draw the pattern. That dot is actually false. It's an artifact that doesn't belong in the graph. So that's out. Okay, so now you saw how to draw it. Let me get this back out of the way, and we can get back to the business of interpreting here. So this is the ball going up the hill. Now, is there a force that's actually causing this? Yes, but let's back up a moment. Let's back up here. On the previous question, it was pretty easy for us. We looked at the fan cart. Yes, the air is pushing fan cart backward. Okay, fine. That force caused that acceleration. Notice they were both pointing the same way. Okay, let's go forward over here. Which way is the acceleration? Well, the acceleration here clearly, acceleration is always, that's why we do the blinking light diagram, acceleration is always toward the bigger spaces. Always toward the bigger spaces. The bigger spaces here are clearly at the bottom of the hill. So the acceleration here for these dots is down the hill. We'll say the dot acceleration is down the hill. It has to be. It's toward the bigger spaces. Now, it's a good time to decide what direction we're going to call positive. So in this case, generally we'll start with the initial velocity. Well, the way it's going, we call that positive. Doesn't really matter. For right now, let's stick with it. You don't have to choose it this way. But let's say that uphill is positive. So this initial velocity is positive, but this acceleration is negative. Okay, let's keep going. Now, why is the acceleration actually downhill? Well, there's a cause. If you remember, acceleration is caused by force. Really caused by net force, but we'll worry about what that net means a little later on. Something has to be pushing or pulling on it. There is something pulling this down the hill. It is the force of gravity. There is something pulling this down the hill. So we will draw something like this. There's a force due to gravity. Put a little g there for gravity. Before we had F air, here we have force due to gravity pulling this down the hill. Now, I'm going to put this, I don't want to give away too much yet. The force of gravity generally points straight down, but there's a hill in the way. You can't go into the hill. So there's a piece of it. Force, gravity, let's call this component. You don't worry about what that means for now. You worry about that later. That's a force of gravity component. That means part of the force of gravity is pulling you down the hill. Whatever. For now, the force of gravity is pulling you down the hill. Anytime you go sledding, skiing, roll down a hill, run down a hill, force of gravity is pulling you down that hill. Roll your car down a hill. Anyway, good. We have all this business right here. So one thing we can do is, like we did before, sketch our graphs. Let's graph out what's going on here. So we had displacement versus time. We had velocity versus time. We had acceleration versus time. Now, of these, the easiest to draw is going to be the acceleration in our course, because acceleration is always constant. There are no jerks in Regents physics. So what that means here is the acceleration is always a constant. It could be a positive, it could be a negative, or it could be zero, but it's always constant. In this case, it's not zero. In fact, we see there's an acceleration. Further, we see that the acceleration is down the hill. Now, we call uphill positive. If the acceleration is down the hill, well, that's telling you if uphill is positive, downhill must be negative. So the acceleration is a negative constant. I'm going to go out to just here. I'm going to go out to the mid-time, not the full time, because we've only drawn the ball going up the hill. The ball has not yet come back down the hill, so the full time has not yet passed. Okay, the velocity graph. Well, let's see. How does the velocity begin? Well, it begins over here in red. It begins with an uphill velocity, not zero. And we called uphill positive. So it has to begin with a velocity up here. Here's our VI. Now, as the ball ascends the hill, as it goes up the hill, it eventually gets to the top here. This top position up here is actually where the velocity will go to 0 meters per second. It stops moving at the top. You know, this is actually not mysterious at all in terms of your experience. You've seen this many a time. If we watch the ball here and run it in reverse, all right, as the ball is going up the hill, when it gets to the top, it right there stops. So the velocity is 0 at that point. Now, how long does it stop? Well, that's momentary, instantaneous stop. Don't ask that question. It's too bothersome. Anyway, the VI is where it starts and then it ends at the top where it goes to 0. So half the time later, the velocity drops down to 0. Now, some of you might know, oh, we're in Regents physics. That means no jerks. That means acceleration graphs are always flat and velocity graphs are always straight. There are no curves. So that could help you do it. Although the truth is, run slope game. And slope here represents V over T, which is acceleration. But if you jump over here, we see that acceleration is a negative constant. Okay, so connect the two. Slope must be a negative constant. How do you draw a negative constant slope? Straight downhill. There's your graph. Okay, we're at half the time. That's what happened so far. How about the displacement graph? Well, in the displacement graph, displacement is shortcut from the start. If the start is this dot right back here where the ball is, well, then you're starting and the displacement is 0. So I'll put a heavy, I know it's black, the black axis over here, but that's okay. Put that dot there. Now notice the ball goes up the hill. When it gets up to the top of the hill, there is definitely a displacement. It is in the uphill direction. We call uphill positive, which means displacement must end at half the time somewhere up here in the positive. Okay, now you might already know how to draw this. However, slope game is good for your brain as it helps you understand what slope does and represents and all the rest of that, how to use it. Plus, it gives you the truth. Slope of a d versus t is velocity. Now, what do we know about the velocity? Well, so far, the only thing we know about the velocity is that it is decreasing. Now, we've only done half the velocity, but it's decreasing. Maybe I'll lower this down so it lines up. There we go. Slope is v, velocity is decreasing. Therefore, the slope must be decreasing. How do you draw a decreasing slope that starts at the origin and ends up here at a high point? There's only one way. Boom, there it is. There's a decreasing slope. It's becoming less steep. Cool. All right, we've gone through half the problem. Let's go through the other half. What happens? Well, the ball will come back down. What goes up must come down, so they say. So here, the ball's at the top. Now if we go forward, it comes back down. Look at that, gaining speed and laying over the same blinking light spots as on the way up. So, let's go check this out. Like you did in bio or some other courses, it comes down over the same spots. Maybe we'll put little triangles this time instead of circles. So it comes down here, 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 and here. Try to make a triangle so you wouldn't see a circle and a circle and a circle. Anyway, comes down over the same spots. Woo! So there's something to talk about here. Now, I know some of you had trouble with this. Which way is it accelerating as it rolls back down the hill? So this is the acceleration for the triangle pattern. Well, you got to look at the spacing. That's the beauty of the blinking light diagram. Truly, the blinking light diagram, if nothing else, shows you the direction of acceleration. Notice the spacing gets bigger and bigger and bigger as you go down the hill. The acceleration is still down the hill. Of course, this makes sense. The acceleration is still down the hill because the force is still down the hill. Gravity is still pulling down the hill. And so here, there's a debate. Wait a minute, is the acceleration here? Is it on the axis? Is it up here? Listen, there actually is no debate. The acceleration is down the hill. We called uphill positive, which means acceleration must be negative. In fact, it has not changed. The cause of the acceleration has not changed. Boom, there it is. There's your acceleration graph, finished. Don't draw those other dots, they're not right. This is not correct. This is not correct. Okay, let's keep going. Now we need to draw the velocity graph. Velocity graph. Well, starting at the peak, we are at v equals 0. So we're halfway through the problem, but the velocity is 0. So we're going to start right here at the axis. Then what happens? Sorry, I made that look messy. Then what happens? Well, okay. It rolls back down the hill. What happens to the speed as it goes down the hill? Well, you can see by the spacing, it gets faster. We also saw this in the video. The spacing got bigger. And if I rewind this one more time and now play it forward, the ball's crystal clear. And it gets blurrier and blurrier and blurrier because it's going faster and faster and faster. So the ball, which is now traveling quickly down the hill, must end with a higher velocity, must end faster. But it's going downhill. Uphill is positive, downhill therefore is negative. This thing is speeding up in the negative, so we'll put a dot down here. In fact, where this lines up will be, that's your VF. We said this before. That should be a little hat on there. As long as it starts and ends at the same location, how will the VF and VI compare? I'll put a little comment here. As long as the start equals the end, comma, the VF must be opposite direction but same magnitude to the VI. So how do we connect those dots? Straight or curve? Well, we'll go back to slope game. Slope is acceleration. Acceleration is negative constant, still, like it was. So slope must be negative constant. Continue that line. Boom. Done. This should be perfectly lined up. I know it's a little offset there. It shouldn't be. All right, cool. Let's go to the displacement graph. Okay, displacement graph. So we're up at the peak now. And we are rolling back down the hill. In fact, we're coming all the way back down to the starting position, which means the displacement, though it was significant, now drops back down to 0 over here on the graph. What does it look like? We got to run slope game. Slope is V. V, for the first half of the graph, was decreasing. but for the second half of the graph, then v actually increases in the negative direction. You see it goes from something like 0 to maybe -2, -4, -6, -8. It's speeding up in the negative direction. Well, if slope is v and v is increasing in the negative, well then slope has to increase in the negative, which looks like this. Boom. There we go. And so what's worth noting here, there's a few different questions I can ask you. Some are very straightforward. What is the displacement at the end? So the displacement at the end is 0 meters. Came back to the start. There's some other simple questions I can ask you. I can ask you, what is the average velocity over the entire time interval? Well, one way to get that, a very easy way to get that, is right here, using the displacement. Velocity, average velocity total is going to equal the displacement at the end per time, which we just found was 0 meters over whatever the time is, which is just going to be 0 meters per second. Easy. There's another way to get the average velocity, which we looked at on the other page. The other way here is, we'll write it separately in this little bracket. Average velocity total is going to be, like your test scores, your initial velocity plus your final velocity over 2. Now, we already said up here that the initial and final velocity are the same magnitude, opposite direction. So here, Vf is negative Vi. So here you have Vi plus negative Vi, because it's the same thing as Vf. We set it up here, over 2. Well, what's Vi plus minus Vi? It's automatically going to be 0 over 2, which is 0 meters per second. So no matter which way you do it, the average velocity over the entire time interval is 0 meters per second. Another nice question I can ask you is, what is the change in velocity over the entire time interval, the total change in velocity? Now, you could do acceleration times time, but it's not a bad habit to really remember the equation. It's quite simple, because I may not tell you the acceleration, but I might give you the Vf and the Vi. Makes it easy. Heck, I only have to give you one of them. So Vf minus Vi, and if we know that Vf equals negative Vi, well, this is actually pretty easy. Last time we did this on the previous page, we substituted in. Instead of writing Vf, we wrote negative Vi. This time, let's do it the other way. Instead of writing negative Vi, let's write Vf. So this would just be Vf plus Vf, which of course is 2Vf. Before we had negative 2Vi, 2Vf. They're exact same thing. There it is. So be careful. Your change in velocity is not 0. You had a homework question like this. Leave these two questions, the average velocity, change in velocity, were like 10 and 11 on W210. So check those out. So these are some very simple questions you can get on a problem like this, and I'm expecting that you know how to do them. So if I give you a bunch of these like this, it's not, notice the math. This is not a 4-minute, set everything up, oh, good Lord, I better get the calculator. This is quick work. But if you ain't ready, that quick work might seem confusing, or you might land yourself with some foolish answers. So be mindful here of your directions with these vectors. The last thing, of course, is what we did before. And this is good for you to know. When velocity and acceleration are aligned, that means when they point the same way, the object speeds up. Now, let me show that up here. One thing we did not draw up here is we did not draw the velocity vector for the way down. So Vi was this way, but Vf is actually this way. Is your Vf, That's the triangle pattern. Notice the acceleration and the velocity for the triangle pattern on the way down. They're both pointing down the hill. The object has to speed up. That's the point of this comment down here. If velocity and acceleration are opposed, the object speeds down. I kind of like that phrase better, but we're used to saying slows down, so that's what we'll say. The object slows down. Velocity and acceleration are opposed, the object slows down. And then if you look up here, if for the dot pattern going up the hill, the velocity is up the hill. The acceleration is down the hill. They're opposed. It will slow down, which it did. Okay, cool. So you should be pretty comfortable with these up, down, or forward, backward problems. All right.